Thanks a lot for the invitation and for setting up this super exciting venue. What I'm going to talk to you about today, so I'm Olivier Hoenen from ITER organization. I'm working within the science division, which is a small scale division compared to the ITER gigantic scales. And what I'm going to talk about today is our very first steps on the open sourcing of software and software that are developed at the organization, especially IMAS. So that's really for us also a very exciting times. And it's very good that it's coming at the same time than this one event. So before just giving you a tour of what we put open sourcing in terms of IMAS software, I think it's important to introduce what IMAS is. So maybe some of you know already about IMAS or may have heard about it, but maybe sometimes this is not clear what's inside, what it's meant to be used on, etc. So let's start with what is IMAS. So IMAS stands for the Integrated Modeling and Analysis Suite. And that's basically at ITER a collection of physics software that we'll use to support operation and research. So we have in IMAS a set of plasma modeling tools that will be used for the systematic planning and analysis of every ITER discharge. So it's quite a big program. Let me give you a brief history of IMAS. So the design and development started around 2011, 2012 at the ITER organization, Ohio, but it built upon concepts that were introduced before within the integrated tokamak modeling task force in Europe, where scientists started to discuss a common data ontology for tokamak fusion. Then further milestones, we had our first prototype being published in nuclear fusion around 2015, where the data entry, which was version control, started to get a certain number of classes. Then 2 years later, another important milestone is start to be used in production on operating tokamak, on the West tokamak from CEA. And there IMAS was used for the plasma reconstruction chain. And later on, more applications start to appear and be published in IMAS. So I can mention just the heating and current drive workflow developed at the ITER organization and an energetic particle stability workflow developed in collaboration with IPP Munich. Now, what's inside IMAS? So I told you about this data ontology. So it all starts first with this data model that we want to be machine independent and that can be used for code coupling and to be the base of integrated modeling simulation codes. On the top of this data model, we are also providing generic tools to manipulate and access these data structures and data objects. But at the end, our final goals is indeed to not just have tools, but have physics applications that will be used for modeling purposes and that will increase our simulation and predictive capabilities and to use that at ITER. So basically all these bricks glued together, that's what we can call IMAS. But the important bit is really it needs to understand this data model, which is really at the core of this software stack. And at the end, the target are physics applications. So let's dive a bit more into the data model. What are these characteristics? First of all, it allows to cover both simulation and experimental data. Inside this data model, we are structuring data objects in what we call interface data structures or IDSs. And all of this is described because these structures are hierarchical in XML format in what we call the data dictionary. Now, these IDSs, they have been made machine agnostic by design. So such as it can be used on experiments. I told you it's already used at West. We foresee that it will be used, of course, when ITER will be operating, but it can also be used to map existing experimental data. And that will allow us to basically support the validation of ITER applications and IMAS applications on real machine data. And for just here in this table, you can find the results of a survey that we did, I think, in the summer 2023, about how many of these IDSs were mapped at the various tokamaks that answered this survey. So you see that there is like a variety of support already, but this was like almost 2 years ago, and so hopefully things are getting also better now. And now, because of these characteristics of the data model, this IMAS data model also has the great opportunity to, or potential to serve as a data standard for the entire fusion community. Oops, sorry, that's the right direction. So just the data dictionary itself, just a quick look out of it. So from this XML description of each of these IDSs, we can then generate documentation, we can do some code generation. And so this allows you to see, for instance, here, the entire list of all the IDSs for various subsystems, for various types of physics, for various phenomena inside a fusion device. Of course, you can go in any of these elements and then have the full description of any of these quantities with this definition, with their units, with their coordinates, if they are arrays or multidimensional arrays. Now, this data dictionary has strict rules for modifications that are allowed. I think we have different types of IDSs. So some of them are active, noted with these small stars, or alpha. Notice that there are more alpha state than active ones. But we try really to not break the compatibility, and especially for all the active IDSs. But these are evolving data structures, and all these changes are driven by the community and by request done inside our Jira trackers. Now, about the tools that we are defining on top of this data model, we have, first of all, tools for accessing this data. So there are different tools in the community, but the library we are developing primarily at ITER is called the access layer. It provides its API in various programming languages. So you can do codes in Fortran, Python, C++, MATLAB, or Java. You will have an API to manipulate and interact with these IDSs. And this library relies on a core C++ library that allows to abstract the various backend storage that we can use. So we have HDF5 support, MDS+, because it's heavily used in the community, but we can also use UDA, that is a client-server technology developed at UKEA, that allows to do remote data access, or flex buffers if you want to serialize these IDSs in memory. We have then various tools for plotting, visualizing this data, and that again depends on your needs. So it can be simple command line tool in Python using matplotlib, or tools within a graphical GUI environment, allowing to explore the quantities. Maybe you can zoom on it a bit, where you can really see all the quantities and do a plot of simple data or get the data itself. but you may have like more complex data you want to render. There are placeholders to store it in IDSs, and so we also have like a plugin for ParaView doing more advanced visualization. Then for designing complex workflows for integrated modeling, we have tools that are helping there. Also, one simple tool called IRAP that will standardize the creation of Python actors around Fortran, C++, or Java code. And then you can plug all of your Python actors in a script, in a programmatic fashion. And we are also investigating the use of the Muscle3 multiscale coupled library, which allow us then to explore more different types of coupling patterns. So you have different models and there are different ways to interact, which is other. It's not always a simple chain. Maybe there is some scale overlap or like a macro type of coupling. And finally, you made your simulations, you have some simulation results, and you want to store that into databases to share with others and to be able to query and search these simulations from your database for different types of quantities. And so we have also tools like SimDB that allows to do that and plot the results and compare results between simulations. Finally, as I said, most important things are physics applications. The sort of workhorse here at ITER for plasma simulators is based on DINA GenTrack here with H2D to be able to do core edge integrated simulations at ITER. This can also be linked with the workflow to describe heating sources and current drive. We can do scrape-off layer and plasma wall interaction studies with LPS heater and the Smither field line tracing code. We have tools and workflows to do energetic particle studies, and we are also investing into developing synthetic diagnostic models because, as you know, on ITER we'll have really a large variety and number of different diagnostics, and to be able to prepare operations, we need to generate synthetic models. So we are especially interested in having these models in a Bayesian framework that will allow us to use these models as forward models for synthetic diagnostics, and at the same time use it as the base of inference when we'll try to gather ITER data. Now, that's very good. We have a lot of tools and a lot of things that could be used, but can you use it? Do you have access to it? We are getting there slowly. So it has been a long journey that we can put back. So that's at the signature of the ITER agreement, there was like one part of this ITER agreement, the Article 10, that mentioned that the ITER organization and members should support the widest appropriate dissemination of information and intellectual property they generate. Of course, the widest appropriate dissemination could be a bit stronger, so it is still a bit fuzzy. But basically, when the development of IMAS started at ITER organization, everything was stored under a version control system. So we have, and we had also already at that time, a platform based on Atlassian products, but this was not openly accessible. This was all password protected, so you needed an ITER account to have access to this software. And most of this software had a license that were based under a modified 3-clause BSD license, which was not completely, which was not open, basically. Even if the ITER member states, that's a large fraction of the world population, you still have a license that restricts sharing these codes only within the ITER member states. So while more and more people started to want to get access to these codes, around just before COVID, we started to have more and more discussion on open licenses. After the COVID, we were not there yet in open licenses. So we started to put in place additional cooperation agreements, additional web forms that allow people to automatically be registered and request access to various repositories. So more and more people could get access to it, but it was not yet open source. And finally, last year, around November or December, we finally got the green light from our Director General to release the codes developed at the ITER organization under an open source license. And so early this year, we started to move the very first codes on open GitHub under the ITER organization, GitHub organization. What you can find there right now, of course, it's the IMAS data dictionary. So as I said, that's the core part of our infrastructure. It gives you all the definition and documentation of IMAS IDSs. There we have two different licenses. So the IDS schemas definition itself is under a Creative Commons license with a no derivative clause. And the idea there is basically we want to push this data model to go in a direction where it can be used as a standard, and we don't want to end up with like many forks of and slightly different versions of the standards. But we'll see how it evolves and how it can interact with the community. There is a bit of Python codes, which is LGPL, that allows to build documentation and a small command line tool. But most importantly, what we want is to move all of the questions, the discussions, the request for any changes, for any additions, to be done openly, directly on the GitHub platform. And so we are going to move everything that was done before on our Atlassian Jira platform, which was within the community, but it was a closed community because you need to add an ITER account. Now this can happen right now, really on public-sided GitHub pages. And you have, of course, all the documentation and the package available publicly. The next tool we have putting there is IMAS Python. So that's our tool for accessing and manipulating IDSs in Python. That's super easy to install. It's all LGPL compared to our legacy access layer Python interface, which some of you may have used already. This one has no code generation. It's completely parsing the DD at runtime, which allows for the dynamic selection and conversion of the versions. And it has all the metadata. It can do duck typing, lazy loading. You have here an example of instantiating and filling out parts of an IDS for an equilibrium description. The only things at the moment that we don't have on GitHub is that this tool can rely on the IMAS core library, which I told you about before, which allows to do storing the data and retrieving the data from disk. And this is not open yet. We'll come back to it later. But what we have added is the possibility to store these IDSs in a self-described netcdf format. So you can really use it right now, and it has almost the full capabilities. The last tool that we've added on the platform is this Plasma Control System Simulation Platform, or PCSSP, which is the MATLAB Simulink platform that we are using to develop, test, and integrate controllers for ITER before they are implemented in the real PCS and the real-time framework. So that's the three repositories that we have right now. More will come. So we have a simple Python command line tool that we can use for checking validation rule sets on IDS. We have a ParaView plugin that will allow you to visualize complex meshes stored in this generalized grid description in IDSs. And we have this SimDB tool, so that will, it's a small client with also a server with a REST API that allows you to build, share, and explore databases of simulations. Now, what's next? So first of all, and what are the issues that we faced in this? So first of all, coming back to the story of the IMAS core library and why it's not yet openly accessible, that's the problem with software with background intellectual property. So a majority of IMAS software or software that is inside IMAS, especially physics codes at the moment, they are not being developed from scratch at the ITER organization. They existed and they were developed over years within the ITER members. And so they have background intellectual property. So when and if we want to release this software as integrated part of an open IMAS, then we need to have the owners of this software releasing their background IP also open source. And so for that, ITER organization starts sending requests to these code owners, labs, institutes, to ask if it's possible to release the background IP open source. And so we hope that some of these will be straightforward, will get authorization, and that's going to generate or speed up a trend in Fusion. Of course, when you got access to open source codes, that's not the end of the story, right? You can use it, but a key aspect, especially for project sustainability, is to contribute back to this software. So here I don't want to enter too much into details, but basically there are like various ways to contribute back. I hope you're all buying into this. I just maybe want to mention the example of Thorax, because I think it will be presented later today, which is a software pretty open source that we really want to use as a core ingredients for our Pulse design simulator at ITER. Now, you may wonder, yeah, but why I would adapt another code to IMAS, a code that you may be developing, a code that may exist in the community. There may be several reasons for that. Maybe it's because you want this code to be part of the ITER code suite, so the part of IMAS that we reuse for modeling and preparing ITER discharges. It may also be helpful when you want to do benchmarking exercises with similar codes, especially if these other codes have been already adapted to IMAS. And you may see an opportunity to use standardized machine description, and that will allow your code to be more easily applied to different tokamaks or machines. Now, how you would do that, it's a bit free. The most important part is you need to make your I/O understand this IMAS data dictionary. That's the first and the most important step. Then you can have like a very non-intrusive adaptation by just developing a wrapper around your code. And this really depends on your targets. But of course, the important bit also anyway is to get a license for your code. Very often in the community, I see a lot of codes and they don't have a license or a clear license, or it's difficult to understand what is the license of the code. putting the license and clearly available within the code repository. And of course, consider an as open as possible license is key there. And having codes adapted to IMAS is great and it's a good thing, but having the data is also fundamental here. So here we want to have data adapted to IMAS to help preparing interoperation that will help us to validate the applications, but it will also help getting people trained on the application, because at some point we'll need people not just from ITER organization, but coming to ITER and operate the machine and prepare the experiments. It can help establishing multi-machine databases, and it can also be used simply if you have like need for additional modeling capabilities on your own device, and if IMAS has a specific tool that will help you in that aspect. So of course, this is a major effort. It's a very large effort. It involves experts on a given device. And of course, this is a sparse resources. And it has caveats, like sometimes we have to bring non-backward compatible changes into IMAS data dictionary. So you have to adapt also your mapping. So we know these caveats. We think that, identifying success stories, have more targeted efforts, and sharing more the mappings, the experience, especially on open platforms. And there are examples already. So for instance, from UKEA, we have already open mappings for MAS2 and JET. This will help on the long term. Finally, before concluding, we know that all the situation is not perfect yet. It's still too complex to some extent. So you can see in this movie, I hope, the evolution of the number of IDSs. So each color is a different IDSs. And there you see the nested structures of the IDSs. So the more rings you have, the more nested elements you have. And the more widest this color is, then the more quantities you have defined. So this is a large and complex data model. We are trying to simplify it, or we want to try to simplify it using more standard definitions of geometries, grids, relying on things that have been done outside of the Fusion community that will be already be used extensively in other communities. We want to better separate the data model from the interfaces. That should also help us really reducing the complexity and be more flexible overall. And we want to avoid really non-backward compatible changes. These are basically by design impossible to introduce in an active IDSs, except we have a major data dictionary update. So we want to get more IDSs in active state. And at the same time, we know that if we want to have that as a data standard for the entire Fusion community, we want to get more involvement from the Stellarator community. We know that some IDS leans towards tokamaks. They use the axisymmetric description. And we want to focus more and really ease the use of the data. Initially, a lot of focus was on data producers, but the data is basically being written once and fully being read a lot of times. So we really want to now target more the data consumers and the ease of use. Okay, and to summarize, so finally, after a few years of discussions, the organization can right now make the software it develops under an open source license. We started to put a few of them already on Open GitHub. More will come. This will be a gradual effort. There are a lot of software in IMAS at the moment. For some of them that was developed outside of IMAS, we need, first of all, to have the owners of the background IP to agree to these open licenses, but this hopefully will participate to the trend in the community to get more and more codes on the open source licenses. And then at the end, our vision on the long term is really having the open IMAS metadata available. That will be a step forward towards implementing a fair data principle for the community. And on the long term, we increase the reuse of codes, the contributions overall, the code quality, and we facilitate the engagement from people outside the Fusion community, like specialists in AI and machine learning, for instance. And with that, I'm thanking you for your attention and letting you see some of the links and resources for this talk.
Thank you very much, Olivier. We have about 1 million questions in the Q&A, so I'll try to go very quickly through them. It's very nice that you're using open source software for slides as well, I noticed. This is using the rebuild.js library.
They are on GitHub, on my GitHub account. I will send the link later. Yeah, so that will be accessible.
It's very nice. So we have, I think, a couple, 2 questions here. One is from James Cook. What happens if a copyright owner doesn't allow the open sourcing of their code within IMAS core? And linked to a question from Dave, what kinds of responses are you getting from code owners? Are the majority willing to open source, or are they resistant?
We have different cases. So, okay, first, what happened? Well, what happened is basically if we just have a little bit of generated IP on top of the background IP license and the owners doesn't want to have it, then we cannot do anything. We can continue to ask, and hopefully things will change. But then at some point, it will be a showstopper. So what will happen is basically we are going to, if we believe that is also a problem for our infrastructure, then we are going to seek for replacement. There must be another code somewhere that maybe have the same capabilities and that is more willing to go open. Maybe it's not yet in IMAS, but then will involve effort to getting adapted to IMAS. So that's what I think would happen. And the second part of the question was...
So far, what kind of response have you had from code owners? Are they been willing, or is this open sourcing?
We have a few positive answers, and we have a few yes, but you need to describe. So, for instance, with the European Commission, which under the umbrella, some of these have been developed, especially inside the ITM effort. We are still interacting. So at least there is response and quick response. So I think we can iterate on that, and we can hopefully within the next few months have a good answer for most of them.
Thank you. Another question from Dave is, do you have concerns about license compatibility among the many components in or integrated with IMAS? For example, the question of POSIF license versus copyleft licenses.
That's maybe a problem. Yeah. What we're trying to get is really, at least for all of the software that we are developing, trying to put them under LGPL license that gives full flexibility for using it, either inside. I mean, it's not like the perfect open source license if you ask the GNU community, but basically it gives a lot of the freedom. It's not also an MIT license that gives all the freedom possible, but yeah, that's something we need to see and learn by doing.
I believe that'll be one of the topics of the panel discussion later today. There's another question from Peter Hill. Is there any existing tool for converting legacy formats to and from their equivalent IDS? And there's an example of a code I do not know. EQDSK. I'm not a plasma physicist, so apologies.
Okay, that's the story of this de facto equilibrium file format used in the community, which exists. And then we have several tools in the community that allows to convert GEQDisc files into equilibrium IDS. So these tools exist already. Then the idea is if people have a small file format for a code, for a group of codes that exist and want to invest effort to get conversions to the equivalent IDS format, that will be very much welcome.
I believe there's already an answer from James Cook of a working open draft PR doing this. Maybe one last question, and then I'll let you answer all the others later on. We can also download the Q&A to answer all the questions, but there's one from Benji Smith. What is the current timeline for open sourcing the visualization and workflow tools in IMAS?
So for the visualization tool, the one that is for general grid description, so this ParaView plugin, it should be a matter of a few weeks. So this one is completely on IP, so we can do right now is just that we need to take the time to put it, and sometimes we need to change the name because we want to have it easily on PyPy, and there is a name clash. So we need to consider all of that. So it will come very fast. The workflow tools, this one is so IRAP. So Muscle3 is already open source, so it's available. You can get it. And the other one called IRAP, this one we need to adapt it first because the current one rely on the previous legacy Python access layer, and so we need just to update this part to get it available with IMAS Python.